Now we're moving into the quantum mechanical model. We'll talk about the 4 quantum numbers and start to get into this electron configuration. So quantum mechanical models, so first of all, get a quantum mechanical model gives us our best understanding of where the electrons are located. Remember, we already know the electrons are located around the nucleus. We just don't know specifically where. So the quantum mechanical model helps us to do that. Scientist Erwin Schrödinger, his mathematical equation, or solution, actually led to our quantum mechanical model, the most prominent model used today, and it gives us our best understanding of where the electrons are actually located. About 90% probability we're going to find these electrons. So we know, like a great example of here is we know in an airplane, you know the blades, when the engine turns off, you see propellers. But when the engine's running, the propellers are turning at high speed, we don't actually see the individual propellers, we just see a cloud in which you're located. And that's really where we are, same concept, that's where we are with the electrons, with their understanding there. So we have about 90% probability where we're going to find them. The more dense an area, like in this area, the more dense it is, higher probability. When you get to the outside, out here, and it's less dense, out in this area, around here, less dense, that area is going to be where you're going to be less likely to find it. But again, we're dealing about with a 90% probability of where these electrons are actually located. The atomic orbital is often thought as a region of space with a high probability of finding electrons, and each energy sublevel or subshell corresponds to an orbital of different shapes. There are 2 shapes I do want you to know, and the shapes are for 2 sublevels, or we call them houses, S and P. S is spherical, kind of easy to remember, and P was our dumbbell. Now the S is just a simple sphere. It just gets larger and larger and larger. S, 1S, 2S, 3S, 4S. We do know that the P remember we talked about the P sublevel has 3 different houses. And remember, it can travel in the X, it can travel in the Y, or it can travel in the Z axis. So again, we know 2 electrons per room, right? Or 2 electrons can travel in any track at any given time. So a P holds a total of 6 electrons. Remember that? That's our P. The D has actually five different pathways or orbitals of travel. We call it the 5-bedroom model. So if 2 electrons in each of those at any given time could hold a maximum of 10. I won't have to go after the shape of 5, nor will I go after the shape of F. To see the shape of F, you need to look at it. Just look on that online. The F, there are 7 possible orbitals, and you'll see them as a 3-dimensional structure. So we'll talk about the quantum numbers. The quantum numbers are used to give an address to these electrons. The 4 quantum numbers are actually 4 letters. I won't go into the numerical value of them. The only one I actually will, that would be my N. That's my energy level, and we go from energy level 1 all the way up to energy level 7, as high as we go as of right now. The second quantum number is represented by the letter L, and this is my sublevel, also called subshell. In our analogy, this was the house, right? In our analogy, this was the house. And so we had 3 houses. We had the S, we had the P, we had the D, and we had the F. So those are our houses, S, P, D, F. Those are the possible houses. Now, the only shapes I wanted you to know, S was a sphere, and P was a figure 8, right? That was our P. Those are the only 2 shapes I wanted you to actually know. So, sublevels. Now, there are numerical values for these. If I said L equals 0, I'm talking about S. If my L equals 1, I'm talking about P. L equals 2, I'm talking about D. And L equals 3, I'm talking about F. I'm not going to get into that, though. Don't panic about that. I'm not going to come back after that. So again, my L equals 0, I'm talking the S. S is simple sphere, and it does 1S, 2S, 3S, it's all it is. It's still an S, it's a 1-bedroom model. Don't worry about this Christmas tree structure. This is the possible charges of my orbitals. I'm not going to get into that. But moving on, the third quantum number is represented by the letter M, and these are the possible pathways of travel. These, in our analogy, these we're talking about the rooms, okay? So S was a 1-bedroom, right? It's just 1S, 2S, 3S gets bigger and bigger and bigger. It's a 1-bedroom. The P was a 1, 2, 3 bedroom model. All of them are a figure 8 shape, traveling in the X, the Y, or the Z axes. So 2 per room could hold a maximum of 6. But the M, we're talking about orbitals. In our analogy, we're talking about the actual rooms. D is a 5 bedroom. F was a 7 bedroom. There are numerical values to these, but I'm not going to get into them. Don't worry about that. The last quantum number is represented by S, and that's going to be our spin. And what we do know is this, that any two electrons within the same room must have opposite spins. We do know they spin in the positive half, or in some spin in the negative half. But we do know this, if they are in the same room, that's where I put arrow up and arrow down, because they have to have opposite spins, and that's what the arrows actually help us represent. Now for an address, this is how it works out. These 4 quantum numbers give an address to these electrons, about 90% probability where we're going to find them. For example, it's like you live in the US, well, whereabouts? Well, the energy levels tells us we live in the state of California. The sublevel tells us what city we live in, Fullerton. The orbital gets more specific in what street in Fullerton, Dorothy Lane. And then the spin tells us the house number is 2200 East Dorothy Lane. So that's where we are at Troy. But again, that's specific. Now we know what's in the house. We have a high probability it's in the house. About 90% probability it's in the house. But is it always in the house? No. If you're going to come and find Mr. Gower during the day, where are you going to go? You're going to go to room 908 to try to find me. Am I always in 908? No. High probability I'll be there, but I'm not always there. So that's kind of where we are with the electrons. But we are now going to give them a home. And so that's all we're doing with these 4 quantum numbers. Now let's talk about this. So S, sublevel S, that's my house, is a 1-bedroom model, or has 1 orbital, therefore can hold a maximum of 2 electrons. My P model is my 3-bedroom model, or has 3 possible pathways of travel, all in a figure 8, each holding 2, holds a maximum of 6 electrons. D is a 5-bedroom model, 5 possible orbitals of travel, 2 electrons per orbital, holds a maximum of 10. And F is a 7-bedroom model, or 7 orbitals of travel, each orbital handling 2 electrons, holding a maximum of 14 in NEF. SPDF 1357. SPDF 1357. Now my energy levels. So we're going to only go up to energy level 5. We can go all the way up to energy level 7, but we're not going to. So energy level 1. Now energy level 1 is very, very small. Okay, so remember I have a nucleus in the middle. And I have my first energy level around that, then I move out, and I move out, and I'm moving out. And so my energy level is out here. So as we move out, we get larger and larger and larger. But the first energy level 1 is so small that the first energy level 1 can only handle the S. So I put 1, so it's my S, and it's an energy level 1. Energy level 2 gets large enough that it can handle the S and the P. Now if you remember back to the P block, the number to the right of the P block, the first number we saw was number 2. Energy level 3 is large enough, and now it can handle the S, the P, the D. Now if you remember, right after 4S came 3D, so D doesn't show up until the 3rd. And then remember, the F block at the bottom starts out with 4F, 5F, so the F does not show up until 5, or until 4, excuse me. 5G is the next one, but we're not even there yet. But it is set up if we are to go there. Electron configurations. Again, a couple of key terms to know here. Make sure you are aware of these terms. Great terms to know. They love to show up on a test. Alt-Bau principle just tells us we start at the lowest energy level first. For us, that we're starting at the top of the periodic table, meaning 1s2. That's what it meant for us, starting at 1s2. Pauli exclusion principle is no 2 electrons can have the same 4 identical numbers. They may have the same n. They may live in the same house. They may live in the same room, but they will have opposite spins. Okay? They will not have the same spin. So they will all have unique 4 quantum numbers, unique every single electron. Hund's rule tells us that electrons will fill. Let me go back there. Hund's rule tells us electrons will all get their own room. So remember we talked about this. If I have a P sublevel, remember P sublevel or P house has 3 bedrooms. I have to show them whether I fill them or not. So if I have a P, I have 3 rooms, 1, 2, 3 electrons. They would all have their own room. It's not until I have 4 electrons living in the P house I double. 5 electrons I double twice, and 6 electrons I have to double a 3rd time. But initially, every electron, first of all, wants its own room. That's Hund's rule. When we draw electron configuration, remember we do the electron configuration was actually a condensed version of everything. The 1 represents the energy level up to energy level 7. S represents the house, SPDF. And the superscript represents the number of electrons present. The orbital diagram tells us the exact same information. So we're dealing with 1s. Again, 1s has 1 room. And I have 1 electron, so I'm going to put 1 arrow. That's all I'm doing. Okay, same thing, just a little more detail. And we'll realize, that's where we realize that the orbital diagram takes up a lot of space. And that's the one where, again, we shorten up, and that's the one where it really helps using the kernel method.